speak, read, and prompt high-fidelity text-to-speech with minimal supervision. And when we read the paper, we kind of found out that the architecture that they presented, it's simple. It's basically just like two transformer models stitched together end-to-end. And the samples that they released also sounded really, really good. Unfortunately, they only released the paper and the samples, and we thought we give it a shot to basically replicate the paper. We had no previous experience with TTS, speech, or even with training big transformer models. And as I said, this is basically our journey. Let's see if that works.
Hello, FOSDEM. This is the first demo of WhisperSpeech, a fully open source text-to-speech model trained by Collabora and Lion on the Joules supercomputer.
This is basically just like one example that WhisperSpeech is able to produce. And we think it's basically on par with the text-to-speech that you get from Amazon, Microsoft, or Google. Previously, I basically said that we built WhisperSpeech on top of SpearTTS. That's only like half of the story. We actually built WhisperSpeech on top of some amazing open source projects, mainly Whisper from OpenAI. That's also like where the name WhisperSpeech comes from. Encodec from Meta, which is the neural codec, and Vocus from Gemelo AI. We also, in the process of implementing WhisperSpeech, we read a bunch of papers from different AI labs, namely, of course, SpearTTS from Google, MusicGAN from Meta, and Tensor Program 5 from Microsoft and OpenAI. So this basically shows you the rough overview about the architecture of WhisperSpeech. So on the left, of course, it's a text-to-speech model. You have the input text, which is then fed into the first transformer model, which kind of creates a phonetic representation of your input text. And since it's kind of difficult to figure out emotions or prosody from the text itself, we also embed this into the phonetic representation as part of the first transformer model. Then the phonetic representation is fed into the next one, which then actually creates the actual speech. It's still compressed speech, but it's speech. And we also, since the text doesn't give you anything about the speakers, emotions, whatever, we also add speaker embeddings on top of it. And then we apply the Vocus vocoder to actually get the audio out of it. Now, I mentioned that we kind of get a phonetic representation, and the phonetic representation actually comes from Whisper itself. And Whisper is a very easy just encoder-decoder model. And if you just look at the right, the Whisper decoder just takes the Whisper features and creates the text tokens with varying speed because, you don't really have an idea from the text itself, but from the audio sample, how fast the speaker is. And on the left, of course, you have the input speech, which is like an audio file, goes into the encoder, and this actually creates the phonetic representation. And what we did is we trained a quantizer in between the encoder and decoder to not only reduce the number of features, but also to kind of force the encoder to focus on the phonetic representation. Now, we basically have our architecture in place, and this was basically our plan, how we can basically train WhisperSpeech. Starting from the right here, we have the speech waveform, which is just audio files, and you can find a bunch of audio files on the internet. The problem is, if you want to train a model, like a text-to-speech model, you also need the transcription. Luckily, we have the OpenAI Whisper model that can take audio and create the transcriptions for us. And then we just do the reverse. We have the transcriptions, and in the training process, we just use the audio file and the transcriptions to train it. But when we actually started the training process, we kind of figured out that it fails on all fronts. And let's just go through the different parts. Starting with the speech waveform. I mentioned that we just used audio data. Luckily for us, there's like this really great data set out there. It's called Librelite. It was released by Meta. It has 60,000 hours of English speech in the public domain. But then, like the first problem that we encountered was it comes as a single 3.6 terabyte tar file, which is kind of dumb. Just if you want to download this, and if you can like saturate your 200 Mbits like connection, it takes you like 5 hours. But if you're like us, you want to try out different things. You don't really like download it like once. You download it like multiple times. So it's a problem. If you want to unpack this data set, it takes like over 8 terabytes on your SSD. So you have the data available. The other problem is read amplification. So the 3.6 terabytes are actually 220,000 files. And the Librelite dataset, as I mentioned, it's basically audiobooks. So they're kind of like split up into 2 chapters. And one chapter has around like 16 megabytes on average. And in machine learning, what you want to do is you kind of want to randomly access your data. You want to shuffle it. You might want to just extract like 30 seconds out of like a single chapter. So on average, you kind of have to read like 8 megabytes, and the rest is just waste. And if you do the math, if you want to train this, you kind of have like an SSD that can read like 6 gigabytes per second. You have like 8 GPUs and like use a batch size of like 32. You arrive at like 3 iterations. In practice, what we have seen is more 0.5 iterations. Because like you get like file system overhead and just like the system overhead in general, which is really, really bad because like you would wait like months to just finish like a single iteration. Luckily for us, there's this really cool project, WebDataset, from TMB Dev. That's the GitHub user handle. And what the WebDataset actually allows us to split up our 3.6 terabyte file into like charts. It's just like splitting up in multiple tar files. And we split up the whole data set into 623 5 gigabyte chart files. And the web data set then allowed us to read 8 random charts sequentially and also shuffle. And if we do the math again, like we basically arrive at 330 iterations per second on the same system. And that is something that you don't really see because like most people just maybe deal with like a gigabyte of data and that's it. And it just fits in RAM and you don't really have a problem, like you don't have copies whatsoever. But if you deal with like a lot of data, large data, the disk actually becomes a bottleneck. So now we have a way to read our audio files, our audio books. Next thing is that we need the actual transcriptions, right? We needed to train the whole WhisperSpeech model. And luckily, as I said, we can just use OpenAI Whisper. It's like a state-of-the-art model. But if we actually use it just like the plain Whisper model that OpenAI released, it's like 50 times faster than real time, which if you want to process like the 60,000 hours, it takes you 1,200 GPU hours, 50 days. I'm not waiting like over a month to kind of get the transcriptions, especially if you mess something like up along the way. You probably do this like multiple times. So make it faster. You can use batches. You can also use faster Whisper implementation, which is using the same model, but just like a faster implementation. You can also switch to a smaller model, which then basically puts it down to like 78 GPU hours, which is still like 3 days. But remember, we are using WebDataset, which allows us to parallelize this across like multiple GPUs. So if you do this across like 100, for example, you can kind of process the data set in under 1 hour. And that not only works for the transcription, but also for voice activity detection, speaker embeddings, and so on. Now we have the transcription. Whisper is like kind of a state-of-the-art model, right? But we encountered several problems. One of it is like we also get timestamps from Whisper. But what we have seen is that they're off by several seconds. Luckily, it's kind of consistent, so we just applied a constant offset. What was even more puzzling was that in the transcriptions itself, there were some parts missing. And as I said, we're using the Librelite dataset. And this is like an example. Like if I hear, like if I'm listening to one of the chapters, it says like chapter 5 of the Things in Our Garden by Arthur Random. This LibreVox recording is in the public domain, and so on and so on. What Whisper heard was basically this. So it ignored the first part completely. And we kind of like, which is odd because like you want to train something like on top of it. And we have a really good idea like how this happened. So basically OpenAI, it's very likely that they use the Librelite dataset. It's about like 10% of the whole dataset, so it's not likely that they ignored this. But they also needed the transcriptions, right? But what they did was basically they used forced alignment and the actual ebooks from Project Gutenberg. So they aligned the text with the audio. But in the ebook, there's no like chapter 5. You don't really see this. Even like the same for footnotes as well. So what we do to basically fix this, if you just ignore the 30 seconds, the first 30 seconds. Now, like to this training itself, just a tip from me, what's the most important thing when you need to solve a difficult problem? And it's basically iteration speed. I'm just skipping this because like I'm running out of time. But yeah, what does it mean in our case? So if we want to train like a large model on like 80,000 hours, on 1,000 speakers, on like 96 GPUs, we take like 6 hours to train, which allows me to basically train two experiments per day, one in the morning, one like after lunch, which is not really great because like if you're like us, you want to try out like a lot of different ideas and like 99% of the ideas are garbage. So what you do is just you train it on a very small data set, single speaker. You can train it on the 4090 in 15 minutes, and that allows you to train basically 48 experiments per day. And then like, you just like train a little model, like add some more depth and profit, right? Now the last part, I mentioned like you need GPUs, 96 GPUs, 100 GPUs. So during our journey, we basically explored like different companies. We started with like DataCrunch, Lambda Labs, which kind of give you like reasonable pricing. But the problem is that usually you can only get like 1 or 2 GPUs, so they're overbooked. Another interesting platform is FOSDEM, where basically users provide their GPUs that they have under the desk. It's a lot cheaper, but the problem is like bandwidth, and they also don't support like network drives. And again, like we have to download the data set like multiple times, like you have machine crashes and all of this. And something that we figured out later was if you do like open source work, you can talk to the Lion community, and they have access to like the Joule supercluster with a lot of GPUs. And then, yeah, you basically profit.
There you go. Give them a round of applause, everybody. Good ending.